Alright, so in this section we're going to look at some multiplication rules. So we just did the addition rule. We're going to look at some multiplication rules, and we'll see how these work. Now, there are actually two different multiplication rules, and you have to use whichever multiplication rule based on whether you have independent or dependent events. Now, the assumptions here, think about having sort of two experiments back to back, or sort of two traits that you're looking at back to back. Okay? Dependent events are things where the outcome of the first affects the outcome of the second. And independent events are when the outcome of the first doesn't affect the outcome of the other. All right? So let's look at some examples to think about what's independent versus dependent events. So if you look at something like gender and testicular cancer. So imagine my experiment is picking a person out, and we're going to collect two different pieces of data. We're going to collect what gender they are, and then whether they had testicular cancer or not. Now, obviously, well, it should be fairly obvious that gender does have some sort of influence on the chances of them getting testicular cancer. If they're male, the chance that they have it is going to be one number. I don't know, let's say 2%. If you're female, chance you have testicular cancer is about 0%, right? So the probability that you have testicular cancer given that you're a male is different than if you're a female. Now, if we did gender and flip of a coin, so if you were male, the chance that you got ahead would be like 0.5 or 50%. If you're female, the chance that you get ahead is 0.5 or 50%. So notice that the gender didn't affect the outcome of a coin flip, right? And gender is affected by certain things, not affected by other things. Basically, anytime we have two groups where we have different probabilities of getting, well, in this case, testicular cancers, anything like that, then they're going to be dependent events. So gender and testicular cancer, those are dependent. Gender and the land of a coin, or excuse me, flip of a coin, oops, I can't write today. Are independent. Okay? So if you look at things like first roll of a roulette wheel versus the second roll of a roulette wheel, well, no matter what the first roll outcome was, the second roulette wheel is going to still have the same odds. It's going to be 1 out of 38 of getting your number, or whatever how big the roulette wheel is. So these are going to be independent, the two rolls. Now, if you have children, well, if your first child has some rare disease, your second child may or may not have that rare disease, but the probability of them having that rare disease is definitely dependent. All right? They're more likely to have the disease because probably they share some of the same genetic traits as the first child, or at least they share the same parents at least, and that gives some dependence to that. So anytime the probabilities are different, we have, excuse me, when we split two groups, we will have dependent ideas. Now, we're going to go over the independent multiplication rule first because it's the easy one. All right? If I say, what's the probability of getting A and B? So what's the probability of getting a male and a tails on a coin flip? Well, probability of getting male, picking a male person, and getting a tails on the coin flip is the same thing as take your probability of being male, multiply it times the probability of getting tails on the coin flip. So if we have a group and the probability of being male is probably close to 50%, probably getting tails 50%, probability of getting a male and flipping tails is 25%. All right? So here's what I want you to do. It turns out that, again, we said roulette wheels are independent ideas. The rolls on the roulette wheel are. So we're going to take a standard roulette wheel. Roulette wheel has 38 slots. 18 of them red, 18 black, 2 green. So I want you to try to figure out what's the probability of getting 2 greens in a row. And then find the probability that you roll 2 reds in a row. Excuse me. So push pause on the video and calculate those things. Alright, so hopefully you've calculated that. And basically if I said, what's the probability, I'm going to write a little bit notation, of getting green on the first roll and green on the second roll? Well, independent multiplication says that's the same as the probability of getting green on the first times probability of getting green on the second. Now, how I figure out the probability of green on the first roll is I say, well, on any roll, there's 38 slots and 2 of them are green. So 2 out of 38 is the probability of green on one roll. So if I do it twice in a row, I will have 4 out of 1,444, I believe. Let me check that on my calculator. Yep, I multiplied that right. Now the probability of getting red twice, red on the first and red on the second. Well, probability of getting red on the first, there's 18 reds out of a total of 38. 18 reds out of a total of 38. So that gives me 324 out of 1,444. So I want you to try this. Remember, red and black have 18 slots. 2 slots are green, and there's 38 total. So I want you to push pause on the video and calculate the following things. Alright, so hopefully you've done that. This says find the probability of rolling a green, then red, then black. Now I want you to notice that order is important. If I just said, what's the probability of rolling a green and a red, there's 2 options for that. There's red then green versus green then red. So I want you to understand that what we're doing here, we are very much depending on that the order comes green first, red second, black third. That is different than black first, red second, green third, right? So be careful about the order on these things. Not that it's going to matter in calculation, but it is going to matter if somebody asks you the same question without order. So green is 2 out of 8, not 2 out of 18, 2 out of 38. Red, 18 out of 38. Black, 18 out of 38. And since these are independent, we can multiply all of them. Okay? And I got 648 on top out of, well, if I take 38 times 38 times 38, you get 54,872. Now the probability that you roll 3 reds in a row, red, red, red. Well, again, red on the first one is 18 out of 38. Second, 18 out of 38. And third, 18 out of 38. Multiply those. I believe you get 5,832 divided by 54,872. So that's how independent multiplication works. Basically, you're multiplying these different probabilities. Again, these are multiplying. Now, dependent ideas work very differently. All right? Now, there's 2 ways to think about this. I tend to like the formula you see here slightly better. All right? Because this is saying that the probability of A given B is probability of A and B happening divided by probability of B. Now let me give you sort of the other way real quick. Not that this is going to, if I wanted to find the probability of A and, well, let me do it this way. Let me go the other way. We'll go B and A first. What's the probability of getting B and A? Think about this as getting like black on the roulette wheel, then red on the roulette wheel. So what you'd have to do is you'd have to say, well, we take the probability of getting B. But now all of a sudden, my chances on the second spin have changed. If this was dependent, the chances on the second spin would have changed. So we have to take, what's the probability of getting A on that second spin, given that I got B on the first? All right. So it's kind of similar to independent, except for this last piece is probability of A given B instead of just probability of A by itself. All right. Now, if you do some, I don't know, arithmetic to this, divide both sides by the probability of B, divide both sides by the probability of B, then you actually get the thing we have here. It says the probability of A given B is equal to B and A both on top divided by B on bottom. Now there's kind of I've said how this kind of works in multiplication, but this formula, all right, should also make sense in the following reason. If I say, find the probability of getting A given that B has already occurred. Let's take the idea of gender and testicular cancer. So let's pretend B is male. So what's the probability of getting testicular cancer given that a person is male? Now, if I'm given that the person is male, then basically I'm looking out of just the males. And if I'm trying to find what's the probability that this male had testicular cancer, well, I'm looking out of all the males. I'm taking those males which had testicular cancer. So they had testicular cancer and they were male. All right, which gives us the result we want. So basically, probability of A given B, the B goes on bottom and the A and B go on top. A and B. All right. So let's look at this following example. I want you to read through this. There's a lot of probabilities, but I want you to sort of shorthand write all of the probabilities that this problem gives us. And then we're going to use those in a dependent multiplication idea. So push pause on the video, shorthand all of the probabilities that this problem gives us. All right, so hopefully you've gotten to do that. So probability of male is 0.42. Female in this particular group is 0.58. So 42% of this group is male, 58 is female. Probability of picking a blue-eyed person is 0.32 in this group. Probability of picking a male with blue eyes, so that means male and blue eyes, is 0.10. And the probability of picking a female who has blue eyes, is 0.22. Now I want you to notice something about these probabilities over here. All right, it is not coincidence that the probability of getting blue eyes is 0.32, and these two add up to that. Okay, in fact, if this is a real problem, it's always going to add up that way. Okay, because there's only two choices here. We either have males or females. So this lists all the people with the blue eyes. Better add up to that probability. Okay. All right, so first question says, find the probability of being male given that you've picked somebody with blue eyes. So find the probability of being male given that you've picked somebody with blue eyes. All right. So our rule says put the probability of having blue eyes on the bottom. If you remember from the last slide, or if you wrote it down, that'll be 0.32. On the top goes the males with the blue eyes. So that's 0.10. Okay. And by the way, for me, it's perfectly fine to leave your answer like that, to write it as 0.10 divided by 0.32. You don't have to give me the decimal version of that. The decimal version of that is 0.3125, but it's perfectly okay to leave your answer as 0.10 divided by 0.32. In fact, that shows me that you kind of know where these things are coming from. Now, notice that if you switch this, if I say, what's the probability of having blue eyes, given that you've picked a male? Well, that's a completely different question. Okay, so what we're doing in this top one is we're taking all of the people with blue eyes, right? And we are saying, what's the probability that you pick somebody who's male? So there's inside this people with blue eyes, there's males and females, right? So what we're doing in the first question is we're taking everybody with blue eyes and saying, what's the probability of getting a male out of this group? In the second question, what I'm doing is I'm taking all of the males and saying, well, what percentage of those males, or what's the probability that I pick somebody at random, and they have blue eyes? So notice it's sort of a very different looking problem. Okay. Now these aren't the Venn diagrams. I'm just trying to illustrate using some drawings. They're not exactly Venn diagrams. Now, probability of being male, well, that was 0.42. Probability of blue and male, that's 0.10. Okay. So I want you to understand something. That this comes out to about 23.8%, or I'm going to say round it to 0.238. This came out to exactly 0.3125. So notice that you are more likely to pick a male person from the blue-eyed pool than you are to pick a blue-eyed person from the male pool. All right, your probability is higher. Now I want you to do the same thing with females and blue eyes. So push pause on the video and do the same thing with females and blue eyes. Alright, so hopefully you've done that. So if I say, what's the probability of being female given that I've picked somebody with blue eyes? So out of the blue-eyed group, what's the probability of being female? Alright, so this again is out of 0.32. And because we're given blue eyes, female and blue eyes, well, the probability of getting female and blue eyes was 0.22. Okay. By the way, notice that 0.68, this is 0.6875. And if you calculate the probability of being male given blue eyes and the probability of being female given blue eyes, those things add to 100. Because if you have blue eyes, there's only two choices. You're either male or female. The opposite, blue eyes given that you're female, well, that's going to be 0.58 on bottom, 0.22 on top. And again, I'm comfortable with you leaving the fraction as they are, the fractions as they are, but if you want to say that that's about 0.379, or, you know, whatever, that's about 0.379, that's supposed to be a tilde, you know, above the equal sign, then that's fine too. Okay, I'm not too concerned. All right, now I just want to real quick draw a Venn diagram of sort of all the happenings on here. All right, so let's draw a Venn diagram of the situation that we just had. Okay. So here's what's going on. I'm going to, instead of drawing circles, I'm just going to draw males and females. As, all right, since 58%, I'll draw the females have a little bit larger slice. Okay, this is everybody. This is my whole population is the big rectangle. And then we had males. And then somewhere in there are blue-eyed people. All right? And so the types of questions we were asking, well, if I ask for the probability of being blue-eyed, given that you're male, well, I'm asking essentially for the probability of this section inside of the male rectangle here. All right? So, in that case, let me get something. There we go. In that case, if you're given males, I sort of ignore all the females and just focus on this rectangle with the males. All right. Now that is that's a very different problem than the probability of being male, given that you have blue eyes. If I'm given that I have blue eyes, then what I'm doing is I'm ignoring everything except for what's inside the blue-eyed circle. All right? And I'm saying, what's the probability that you land here, given that you're inside that blue circle? All right? So there's sort of three things going on here: males, females, and blue eyes, and that's we're asking. One is asking, how big is this red piece? Let me draw the red the other way. How big is this red piece inside the male rectangle? And then the other one is asking, how big is this red piece inside the blue-eyed circle? All right. And those are two very, very different ideas. I hope that we've seen that.